This is the second episode in a three-part series on designing, developing, and deploying an AI agent that automates incident postmortems. In the last episode, we designed a high level workflow for the agent and then performed a reliability analysis. As a result, we incorporated validations and guardrails to make our agent design more robust and trustworthy. We also defined key data contracts or schemas for creating structure of the information that will flow through the system. We identified tools for collecting evidence regarding the incident that agent will use to create the postmortem. A few key design decisions that we made were to use structured schemas for validation, persistent long term memory to store agents' learning over time, workflow orchestration for deterministic control, and observability for maintaining the performance of our agent over time. In this episode, we will walk through the implementation of the agent using Jupyter Notebook so that we can explore the development process step by step. The first step is to install and import the libraries that we will need in this implementation. We will use LangGraph for agent workflow orchestration, Python's Pydantic library for creating structured schemas and validation. ChromaDB is an open source vector database. We will use it for storing agents' long term memory. We will use LangSmith, which is a developer focused platform for AI observability and evaluation for capturing traces and graph runs in this lab. I have already created a free developer account and set up a project with an API key. If you wish to replicate this, you can create the free account and then come under tracing, create your project, and generate the API key. You will need this to connect from your application with LangSmith. For this lab, we will use Incident Postmortem Analyst Lab project. We will use MCP protocol for tool integration and Amazon Nova Pro via Amazon Bedrock as the large language model. Let us set up some core services that we will need. So here we are setting the model ID, which is Amazon Nova Pro. In this lab, we will use the same model to reason about the tool calls, to create postmortem draft, and to critique the postmortem draft. In real world implementation, you might choose separate model for each of these tasks. For example, you might choose a faster or cheaper model for tool routing and a stronger one for drafting and critiquing. Notice that model's temperature is set to 0. This is for minimizing randomness in the model's response and making the runs more reproducible. We also need an embedding model for creating embeddings for agents' long-term memory before we can store them in ChromaDB. We are using Amazon's Titan embedding model. Then we are setting some unique identifiers for our incident request, such as thread ID, user ID, tenant ID. And then we are creating our LangSmith connection. We are passing the project ID and API key and setting this environment flag for LangSmith tracing. By doing this, we will be able to automatically send traces from our agent graph nodes without any additional plumbing. All we will do is to add function decorators in our agent graph implementation. And finally, we are creating the in-memory checkpointer. This is the component that takes snapshot of the agent state after each node execution. These checkpoints will allow us to resume the agent from a specific step in the workflow. This is especially useful when we pause for human approval and when human approves asynchronously. Graph can load the last checkpoint and continue from there. In this cell, we are defining an instance of ChromaDB for storing vector embeddings for agents' long-term memory. Notice we are persisting ChromaDB in a local path. In a real-world implementation, you will choose some durable storage for storing the vector embeddings. And then we are passing the Bedrock embedding model for ChromaDB to automatically embed any documents that it indexes or the query string before it does a semantic search. In this cell, we are creating an MCP server to expose tools that will be available to our agent for gathering evidence about the incident. In real world implementation, these tools would typically be existing enterprise APIs, relational databases, or vector databases. But because this is a demo, we are implementing a small set of tools with dummy data so that we can demonstrate the workflow end to end. In this cell, we have defined the MCP server and we are writing that MCP server in a file. We can use fast MCP to create an MCP server. And then we have this dummy data for incidents. I have 3 incidents here, INC1001, INC1002, and INC1003. Each of these are for different services, Payment API, Search API, and Identity Gateway. And then we have logs for each of these services for the time windows when these incidents happened. We have metrics for each of these APIs, prior postmortems for each of these services, runbooks which have remediation actions when incidents happen, example action items for each of these services, some of them open, some of them closed, and the deployment logs for each of these. And then we have different functions to expose each of these information types. We've exposed these tools as MCP functions using MCP tool decorator. This will allow the MCP client to automatically discover these tools at runtime and also invoke them using MCP protocol. And then we are running the MCP server. So this is a file. We haven't really run it. We have just created the file. In this next cell, we are creating the MCP client, and in the process of the agent itself, we are running the MCP server. In a real world implementation, you would probably host this server on a separate container or even a separate server on the network. After creating the MCP server, the client is invoking MCP server to get tools at runtime. So here you can see it is able to retrieve the tools that we defined. And we will bind our large language model with these tools. And what that will do is it will send the information related to these tools to the large language model at the time of reasoning about the tool calls. The next step is to implement data contracts that we had designed using Pydantic schemas. The first schema that we are defining here is incident request, which is the input contract. This is the schema that will trigger our workflow, and it has the incident ID, which is something like INC 1001, and the plain text request from the end user. We will use this schema to validate our input. And then we have the canonical schema for capturing evidence related to the incident. We will normalize and map data which is returned by all the different functions that we saw into this standard schema. Whether you have logs or metrics or prior postmortem or even agent's long-term memory, it will be represented as an evidence record. We have a helper function later in this presentation that will map the output of different tools to this schema. And then we have the schema for postmortem draft, which is the output of agent workflow. It includes incident metadata, impact summary, timeline, root cause analysis, a list of supporting evidence, which is of type evidence record that we just created, remediation actions, follow up actions. The confidence model has in generating this root cause hypothesis given the evidence it has. We also have a validator which will ensure that timeline and supporting evidence fields are never empty. If they are, the schema will fail validation. And then we have a schema to capture the output of the critique step, whether the root cause is supported by the evidence, what is missing, any contradictions, any duplicate follow up actions, etc. Deterministic validation results schema will hold results of the rule based validation of the postmortem draft. It will capture validation results, errors, warnings, and whether a human review is required. This is the final validation we will do before sending the output to the end user. In this cell, we are seeding the ChromaDB with prior postmortems, writing policy, and service specific operational knowledge. This kind of information is often stored in agent's long term memory so that at query time, you can do a hybrid retrieval. You can return semantically similar results and also policy or style documents that agent must follow by doing a keyword search. So here we have 4 records that we are saving. One is the prior lesson for payment APIs DB pool exhaustion error. Then we have instruction for using blameless language. We don't want our postmortem to name individual as causes. And then we have instruction for postmortems to be concise, evidence backed, executive readable, and technically precise, which is again instruction for writing the postmortem. And then we have some operational knowledge for identity cert rotation. We are creating the embeddings for each of these and storing them in ChromaDB. When we create agent graph using LangGraph, the shared agent state is the only object that will move between different nodes. And therefore, we have reserved slots in this state for every major artifact that we care about, such as incident request, the memory context that we retrieve from ChromaDB that matches the incident request, tool trace, the tool output, and the evidence records, which are normalized memory retrieval and tool output validation results. We also have placeholders to hold the postmortem draft, the results of critique node, a boolean to represent whether we need a human review, review reasons, approval decisions, run ID, tenant ID, and a decision log where every node will write what it has done or it hasn't done. You might be wondering that the data types for each of these fields are either dictionary, list, or string or boolean. We have not used the schemas that we have created. And that is intentional as raw model output is just text. It may not always conform to the schema. We want to store all that information regardless. Therefore, these types are simple list, dictionary, and string types. We will use schemas for validation. So when we get the draft, we will try to load it into our postmortem draft schema. If it fails, then it fails our validation check. In this cell, we are defining a few helper functions that we will use to implement graph nodes later. Blameful patterns will help us detect any language in model's response that violates the principle of creating blameless postmortem. Required evidence types are supporting evidence categories that must be present in the generated postmortem draft before we can accept it as valid and complete. And then we have some functions for loading tool output or model output as JSON, parsing time string, normalizing a string by making it lowercase and stripping any white spaces. And then we have a function for retrieving memories that are semantically similar to our request. So we are doing a vector similarity search here in ChromaDB. And this function will extract tool call from model's output so that we can make that tool call. This function is converting the memory that is retrieved from ChromaDB into the evidence record that we had created. And in this function, we are transforming the tool output from different tools into evidence records. So if the tool name is get incident ticket, then we are converting it into evidence record. Similarly for output of search logs, get metric snapshot, retrieve prior postmortem, etc. In this function, we are doing a deterministic check which will decide whether the postmortem is a valid postmortem, it can be sent out, or it needs human review. For example, we are checking the postmortem draft for supporting evidence, and if the supporting evidence which is returned by the model has all the required evidence types that we have just defined, if not, we will append missing required evidence types to the errors that we are returning. Then we will check that timelines of events which are returned in postmortem draft are in right order. No blameless languages in the postmortem draft. There are no duplicate action items, and the confidence of model in generating postmortem draft is more than 80%. So this is our deterministic check that we will use to validate our output. Next step is to define prompts for different nodes that call large language model. We have 3 nodes in our agent graph that will call the model, and hence we have 3 different prompts. The first prompt is for the analyst node, which will decide which tools to call for gathering evidence for the incident. This prompt will be used in the large language model call, which is made from the evidence gathering loop. Notice that we are instructing the model to gather all types of evidences for which we have tools. When we make the actual call, we will also send the available tools and their schema. The second prompt is for the draft creation node, which sits outside of the evidence gathering loop, and its job is to create postmortem draft. In this node, we will take the gathered evidence and use the prompt to instruct model to generate a postmortem draft which conforms to the schema that we have created. We are instructing the model to not add any thinking tags, any explanations, markdowns, headings, or commentary, and only return a valid JSON. The benefits of splitting the tool calling from draft creation are the flexibility of choosing a different model for each task and also getting structured draft output. Unless instructed, models typically generate their thinking process in their output along with any structured data. This can create problems when we are expecting things to load in the JSON format. The third prompt is for the critique node, which takes the postmortem draft and checks whether the root cause claim is actually supported. It identifies any missing evidence, contradictions, and flags duplicate action items. Notice we are asking the model to generate the output in schema that we have created. Up till now, we have done the preparatory steps for defining agent graph. We started by setting LLM client, ChromaDB, LangSmith, and memory checkpointer. Then we defined MCP server and created an MCP client for tool integration. We also pinged MCP server to gather list of tools that are available. We defined schemas, prompts, and helper functions. We also defined a schema for agent state. We are now ready to define our agent graph. In LangGraph, a graph has 4 main components. Nodes are functions that perform a specific unit of work. Edges connect nodes and determine which node will run next after a node executes. We also have conditional edges with routing conditions to pick amongst multiple nodes as the next node. And the fourth component is the shared state that we saw earlier. It holds the context for the current run and it's visible to every node in the graph. Every node reads its input from the state and writes its output back into the state. So let us define the function implementations for nodes for our LangGraph agent. We had already discussed the agent graph in the last session, so I hope you have the intuitive understanding. The first node, which is validate input node, as the name suggests, performs input validation. One of the simplest ways an agent can fail is by operating on incomplete or malformed inputs. And this node verifies that request contains the required information. We are basically doing a schema validation here by loading the incident request in the schema that we had created. If the input passes validation check, we will write that input in the state along with tenant ID and a decision log that input validated successfully. However, if input fails the validation, then we will write validation errors and a decision log that input validation failed. The next node is the memory node, which retrieves agents' long-term memory that match this incident request. We call the helper function that we had defined earlier. We save the raw memories, the evidence records that we create by mapping these memories to the schema that we had created, and a decision log entry in the state. If you remember, we had pinged MCP server to gather the MCP tools that it exposes, and we had collected them in MCP underscore tools. We will bind our large language model with this list of tools, and what it does is it provides information to the model about the tools that are available and their schemas. The next node is the analyst node, which performs the initial reasoning step to consider which tools to call for gathering evidence by sending the incident information, retrieved memory, any evidence records to the large language model along with the prompt that we had created. And we are using this LLM with tools client for invoking the large language model. And in this node, we are extracting the raw tool outputs and mapping them into evidence records. We are calling the helper function that we had created to do that. You might be wondering, we did not implement any node for making the tool calls. That is because we will use LangChain's tool node, which does exactly the same. Therefore, we will not create any custom node for tool calling. Notice that we are merging the evidence records with the evidence records that are already in the state. That is because the evidence gathering loop can iterate many times. Model can take more than one iteration to call all the tools. Once the evidence is considered sufficient, the workflow generates a structured postmortem draft that conforms to the schema that we had created earlier. Notice how we are binding the large language model client with the structured schema that we had created. In this node formatted draft node, we pass the incident request, memory context, and evidence records along with the prompt that we had created. The model generates the postmortem draft, and if the draft lacks supporting evidence, we are adding it here from agent's state. We then save the draft and the raw draft generated by the model in agent's state. So whatever is in the return is actually being saved in the agent's state. Also notice that we have the traceable decorator that I had talked about. This decorator will ensure that traces from execution of this node will be sent to LangSmith. We have applied similar decorator in every node. The key reliability pattern that we use in this lab is reflection. Rather than accepting the first draft as the correct version, we ask the model to critique its own work. And that is what is happening in this node, where we are sending the request, evidence records, and the draft that was created to the large language model with the critique prompt. The model evaluates if the conclusions are supported by evidence, whether any important information is missing, any contradictions exist in the draft, and then we load the critique results in the schema that we had created and save it in the state. The next node in our workflow is the validation and risk scoring node, which will determine if a human needs to be involved. This is the output validation that will happen before postmortem is sent out to the end user. Validation node introduces deterministic checks that we had implemented in one of the helper functions, if you remember that. While the critique node used a large language model to critique the postmortem draft, validation node will use objective checks to critique it. And it determines if there are any errors, warnings, low confidence of the model, if the severity of the ticket is SEV1 or there is any missing evidence, then a human needs to be involved. It also tries to load the draft and postmortem schema, and if it fails, it logs an error that validator failed schema validation. And then we have the human review node, where we create a review payload with all the information that human needs to review the draft. We then interrupt the agent and wait for human's decision. And once we get it, we log it in our state. This is where our memory check pointer will help. Once we interrupt, the agent will wait for human to approve asynchronously. And whenever it gets the decision, it is able to resume from the checkpoint. And the last node in our workflow is the memory promotion node. In this node, we are promoting a completed incident into the long-term memory if it meets some validation criteria. We don't want to pollute our long-term memory with any weak, unverified, or low-quality outputs. Therefore, we do a validation check for the quality of the output before we save it in ChromaDB. And that is what it is doing here. We save only the memories that are strong enough to be trusted, where there is a draft that was created, validation must have passed. If there was any human review, then the decision should have been approved, and the confidence should have been high enough for the memory to be valuable. You can see we are saving this memory in ChromaDB here. The next component that we will set up for our agent graph is the routing logic for routing flow between different nodes. So the first routing logic we have is for route after validation, which is route after input validation. If the input validation itself fails, then we want to end the flow. We don't want to process the request. Otherwise, we will route it to the memory node, which retrieves memories from ChromaDB. Then we have another route, which is after analyst. If there is a tools call in the agent's response, then we have to stay in the evidence gathering loop and make the tool call. Otherwise, we are ready to pass the flow to the draft generation node. And then we have the third decision, which is after output validation. If the output validation suggests human review, then we have to route the flow there. Otherwise, we can go to memory promotion. And this is where we bring everything together by creating a state graph. We have specified the agent state here, and then we are adding all the nodes that we have defined above. Validate input, memory, analyst, tool. Notice we are using LangChain's tool node. And then we have evidence extractor, draft, critique, validator, human review, memory promotion. And then we have edges. We start by validating the input, and then we have a conditional edge. If validation passes, we go to the memory node, otherwise, we end the flow. From memory, we go to analyst. From analyst, we again have a condition. If the next node is tools, we go to tools, otherwise, we go to draft. Similarly, we have tools connected to evidence extractor and evidence extractor connected back to analyst node. So this makes a loop here. Draft node is connected to critique. Critique is connected to the output validation node. And then output validation node is either connected to human review or memory promotion. Human review is also connected to memory promotion. And then we end the graph. We compile this graph by passing the check pointer that we had created. Let us visualize this graph. We are now ready to test our agent using this request payload. And if you remember, we had dummy data for INC 1001. We're also setting thread ID, tenant ID, and user ID, which will make our run properly scoped and traceable. We are invoking the agent asynchronously as it calls tools and it makes LLM calls, so that can take time over network. So this is the response that we got. We have the draft in the schema that we had provided with incident ID, title, severity, impact summary, root cause hypothesis, and supporting evidence. We're also printing evidence records from agent's state and the decision log, which says input validated successfully, retrieved 4 long-term memory items from Chroma, evidence inventory has 5 records, evidence inventory has 14 records, which means that evidence was collected over 2 iterations of the evidence gathering loop. Critique node evaluated evidence sufficiently. Validator completed schema and deterministic checks. And then it says because it's high severity, we need human review. Let us look at the traces in LangSmith. Here we can see we have detailed trace of everything that happened. Every node that was executed in this turn, its logs have been sent here to LangSmith. For example, if we want to inspect agent's reasoning, we can check here. This is the input that was sent to the model. And this is the output that it generated. This is the thinking. Based on the incident ticket, the next step is to gather more detailed evidence to support timeline, root cause analysis, and remediation action. And you can see the model chose to call tools for searching the logs, getting metric snapshot, retrieve prior postmortem, etc. So you can troubleshoot your agent's run. You can also send your evaluation metrics to LangSmith and build automation on top. As a next step, let us approve this workflow. And you can see it resumed the workflow. It even tried to save memory in ChromaDB. It actually did save memory in ChromaDB. And if we come here, we should see 2 logs. So you can see this is the second one, and this has the rest of the flow. Let us see the memories in ChromaDB to see if our new memory was saved. And you can see now we have 5 records. This is what we saved. INC 1001 on payment API, checkout requests failed and timed out. So this is an example of how you can continuously save agents learning in its long-term memory. However, do that selectively depending upon how valuable that memory is. You can also check memory checkpointer to see how it saves different checkpoints. Checkpointer has saved the agent state at every node execution. For example, this is the checkpoint ID where next node is memory promotion, and this is what it has saved. If you are debugging and you want to start from a certain point in your workflow, taking that snapshot of the agent state, you can do that using these checkpoint IDs. This is an example of how you can invoke the agent from a particular point by passing the snapshot of the state at that time. The final section of this lab focuses on the evaluation of the agent that we created. Building an agent is only the beginning. We must also implement measures to evaluate its performance and reliability over time. By creating an evaluation harness, you can create a repeatable mechanism for testing any changes, detecting regressions, and continuously improving the agent workflow over time. In this example, I have 3 incidents that I will use to run the workflow. And for each run, I will create a score which is based on the factors such as output structure, evidence quality. Here I'm checking if it has required evidence types, grounding checks, review decisions, and overall postmortem quality. And as you can see, we have the evaluation score that gives us an idea of how well our agent is performing. This concludes this episode where we build an intuitive understanding of how AI agents are implemented. We introduced several reliability techniques in our implementation, including deterministic schema validation, rule based checks, LLM based critique, and human in loop review. We also demonstrated how agent can continuously improve its performance by selectively promoting valuable learnings into long-term memory. As you promote your AI agents from demos to production grade enterprise applications, you must complement the creativity and natural language reasoning of LLMs with proper reliability planning, resilience strategies, security controls, observability, evaluation, and well governed memory management from the outset. In the next episode, we will learn how we can decompose the AI agent that we designed today into individual components and then deploy them. We will also learn how you can deploy enterprise grade AI agents at scale.